going to present Alexandra, and it's about actually a topic where normally she's talking on open source conferences about Linux and all other kind of things, because she's a sysadmin and a service support, and she did already a lot of things, but actually her real love is about mathematics, and it's in these places like the hacker camps that actually she can talk about the real passion, and it's actually the elephant's ants and the introduction to topology. But we will see what mathematics will hold in the next 25 minutes. I'm already quite excited, and I hope the video screen is now also quite excited. Give already a big applause to Alexandra.
Always someone.
Okay. Okay, this is it. Thank you. So, hello everyone. I'm first time at Hacker Camp, and I usually talk at the FOSS Linux conferences, and I thought like, oh no, we need something more like interesting and more diverse here. So this is the first time I'm trying to talk about actually very different topics, and let's do the experiment, and please let me know how this works after we talk. So first, let's learn how to check the slides. Just a short intro. I'm Alexandra. I'm on Fediverse. I worked as a CI, DevOps build release engineer. I work in Red Hat, and my major topic usually is Fedora, CentOS, and RHEL, but we are not going to talk about that. Because before I started to do these things, there was geometry and topology. So I studied geometry in Moscow State University, and I did PhD in geometry and topology. And then I decided that, like, you know, you need something less nerdy, where more human interactions and so on. So I switched to IT. And and when I started working with IT, and people often like ask, like you studied geometry and topology and now work in IT, like do you use anything you studied in your actual job? And I'm like, no, of course I'm not using Fourier transformations, or like you don't need surface integrals to write YAML files. There's all different topics. But this is not what mathematics is for me. It's not just the calculus or just the like complex matrix computations or whatever. So what is mathematics? And there are like different ways to answer this question. So one way I like to think about is that mathematics as a thing, it's basically the art and the science of definitions, of defining structures, of understanding them. It is the art because there is no like easy recipe. How do you create a good definition for an abstract object? There is always like inspiration coming from one area or the other. There is creativity, and there is learning and search for a good thing. It is also a science because once you created a definition, you actually, like once you get inspired and think about some definition, you actually have to create a theory which will be supporting it and which make it useful. Like the definition should make sense. It should actually, the object you define should exist, and definitions do not like live disconnected. You need to know if the structures are actually related to each other and so on. So for me, this is a big part of what mathematician is doing when you're past the calculations and stuff and start to do actual mathematics, is actually thinking about these structures, objects, how many different objects have the same property, how many properties you can discard to make an object more interesting, and so on. But today we're not going to dive more into metaphysics, and I want to just bring one specific example of an abstract object which I like from topology, and my goal would be that everyone in the room understands what this is, and this will be a total success. So let's talk about manifold. Let me start from a different beginning. Consider example. You have some object in some dark room, and you have a torchlight. And you enter that room, and you switch on the torchlight, and at any single moment, your torchlight shows only like tiny piece of an object in that room. You can look at one part, at other part, at another part, and then the question is like, what is this object actually? Like, I can only see it one piece at a time, but what is this thing, which geometry it has? And this is a very big question of topology and mathematics, of differential geometry, is like how much properties I can derive, I can understand about the whole object if I'm only like seeing tiny pieces of it, but like each tiny piece of it. So what comes after that? Which knowledge I can build? And like if you're just looking at that example, this is actually cheating, because when you have this mental model of person with a torchlight looking at something, you have actually quite a lot of freedom. You can walk around. You can bring a ruler and measure some parts of an object. You can like step closer, you can step back. You have quite a lot of freedom and tools already available, because you're actually not part of that object, you're outside of it, and you're looking down on the two-dimensional space in front of you. This is cheating. When we talk about topology, we don't have to assume that the object is just like embedded in this space. We have to think about local topology as we are in there. And so this is why I'm suggesting the perfect representation of a local geometry, the ant. The ant is like, in this idea is like, you do not look down to the surface. The ant doesn't look down, it lives in that surface. And the ant can trace its steps and count its steps. So it has some idea of a local environment, but it doesn't have a big picture. It doesn't have the understanding of a bigger world, so it sits in its local chart. And this is what two-dimensional space is sort of all about. It's a basic building block of a two-dimensional space, because you have this close neighborhood where you can measure steps, and that's it. And then we have many ants living on our dark object in a dark room, and they have no idea what they are living on. So each of them has traced their steps and built a local chart around themselves. And when they're sitting there, talking in their favorite Fediverse channel, and discuss the things like, is our Earth actually flat? Or does it have holes? Or how far one place is from the other? And we realize that they have actually no idea, because each of one of them only has the visibility of that tiny little island around them. And so the actual picture they have is disconnected islands where each chart shows something, but we know nothing about their relative positions or anything else. And this is actually the first step in defining a good manifold. It's defining topological manifold. And this is an actual object in differential geometry. It's not something, some toy or whatever. It's topological space. It's the space where in the neighborhood of every point you have some local understanding of what's happening. And that's all you know. You don't know anything else. And this is a good starting point, but then you need to learn more about this stuff. And so sometimes those ants actually meet by some reason. So the shape where we're sitting on somehow provides them the way. And they can meet like this, Or we can meet like this. Like before we meet, we don't have any common reference and we do not know the sizes, we do not know the distances. Whereas like red ant can have its own measure of length, and it measures length in the red ant feet, and the blue ant measures the length in blue ant feet, and then they meet and they're like, what we're talking about. So in this tiny overlapping area, once we actually meet, this is where we have to learn how to translate the language of one ant to the language of another. And again, officially, in official geometry, this is called transitional functions between two charts. This is a way how you transform coordinates given on one space onto coordinates given on another space. And any two overlapping charts have this area where we need a definition of a mapping function. There should be some way to translate the coordinates, to translate the language, translate anything basically like the different charts know about themselves. But the thing is that there are certain rules. You cannot have just arbitrary transitional functions. For example, if you have like established that blue ant is so much bigger than red one, and then you add the green one, which is bigger than blue on the overlapping area between blue and green, and then that green has different overlapping area with the red one. And it must follow the same rules because different relationship which you establish for different overlapping areas needs to align. If you get to a same area through different paths, the result should be aligned, and the topological manifold, which has all these transitional functions defined in a way that they can correctly align with each other, this is what we call smooth manifold or differentiable manifold. This is the manifold which is with a good quality of chart coverage. And not every manifold has a chart coverage with a good quality. It's an actual step, it's an actual evolution of a manifold to get to the chart where the things are aligned in a good way. And this structure gives us a lot of freedom and a lot of useful information about the manifold, because once we have these transitional functions, we have possibility to connect different places on our big manifold with a set of charts, each overlapping with the next one. And through the set of charts, if we have defined something on this part, and then we come to the overlapping area, we use transition function, and we translate our concept into a notion on that intermediate chart. We move around the intermediate chart using the language of the intermediate chart, get to the next overlapping area, translate again, and move further, and so on. And so we can, basically by building those paths, we can reach any connected point on our manifold. And this definition of this concept of a differential manifold allows us to, by this property, it allows us to build like a whole lot of new structures on top of it, because we can define the concept of length, and we can define it in one part, translate to all the other possible parts, and because transitional functions are aligned, and by some other conditions, this length will be completely defined on the entire manifold. We can define an object like orientation. Like an ant can define where the up is. And then that concept of up, which didn't exist before, we can again move it along the path, and by moving it along the path, we translate it and bring it to the rest of a manifold. given that there is certain alignment, because there could be non-orientable manifolds. And we have this tools in our toolchain to open this up to basically build entire geometry on that single definition, because it's so powerful, because it's so constructive. And yeah, this is where I like it, the concept here, because if you know the parable of a blind man and elephant, then the parable says, blind men try to understand what elephant is. And so each of them touches a certain part of an elephant and try to explain it, and then they fight because each of them touched a different part and they completely misaligned. And this parable is a very classical philosophical thing and so on, and the main message there is yeah, people have different perspectives and people can have completely different understanding of the same object because the global object is so much bigger. But the thing is that parable is just states the fact, yeah, there is a problem. What I like about the concept of the manifold is that it acts as a solution. It's yeah, you have a big global object, and at every moment in time you observe only one piece of it, and you can have misalignments, and you can have misunderstandings, and you don't have a common reference point, you completely disconnected, but you have a way forward. First, you need to reach your neighbors and find the overlapping part between you and your neighbor, and on that overlapping part, you need to establish a transitional function. And once you establish a transitional function on the overlapping part, you can extend your shared understanding to both parts. And then you find another neighbor, and again, find the overlapping part, establish a transition function, and transfer the knowledge further. And yeah, this is a very common moment, at work when you sit in a meeting with 30 people and they are saying no, this feature is completely deranged, and this feature is completely bloated, and no, we need totally different things. And you sit there and folks, have we built our transitional functions yet? How can we talk about things without establishing this global structure? So this is the object I do use often, even though, yeah, it doesn't calculate anything. And yeah, as I said, these tools give us a lot of possibilities to describe common manifolds, and you can think about manifolds yourself. You take a sphere, right? Sphere is a manifold with two charts. We just go as north and south pole. Or you can say donut. Donut can be covered by 4 charts. Or you can say just a piece of paper. It's a surface. It's covered by a single chart. So this is the functionality which gives us the shared way to describe all these common objects. And as a bonus fact, we actually can use this to prove a certain more interesting properties. And for example, there's smooth, compact, connected, oriented, two-dimensional manifold, which you need to piece together as a manifold which doesn't have, where all points are connected and which doesn't have edges and so on. And using this definition, we can actually prove that any such manifold is a sphere with attached handle to it, or multiple handles to it. Take a mug and add a handle, take a mug with 2 handles, take a mug with 15 handles. This is all what it is in the world of two-dimensional manifolds. So, I hope you liked this short introduction. There's more into the topics of geometry, and yeah, it doesn't need formulas. So, take a look and enjoy. Questions?
questions?
Thank you for your presentation. I have a question about transition functions. Is it by definition smooth transition in the area where have no idea about, or it's like we have to prove it because it can be, I don't know, black hole between ends and can be anything.
Yeah. So
Like defined.
this is where, like, as I mentioned at the beginning, we actually play with the definitions, and there's not a single definition defined forever. It's like for which purpose we consider the definition. So we can relax the definition and describe all objects with non-smooth transitional functions if we need something out of that. Or we can, like, say manifolds with transitional functions are more interesting because they give us more and we can build a theory on top of it. So for the smooth manifold, transitional functions needs to exist and needs to be smooth, needs to be differentiable in both ways. It's like this type of manifold which is used for this type of theory. There are different types of manifolds and there are different reasons to use them, and for them you give definition in different way. So you have your own goals, and then when you have some random object, you need to prove which definition fits that object. But you need to start from a different side.
Okay, yeah, thanks.
Yep.
Hi, this is there, yeah. In staying with the parable of the many ants that are walking around and not, on the earth and not knowing where they are, when a bunch of local, like, neighbors of ants see each other, they can get it so the scales or how far they are, but they will still probably think that they are on a flat earth. And until they start to extend, and it still looks pretty flat, but eventually when they get too far enough, they will see that actually this doesn't really work. And at some point, they need to have a different transitional function to say that, oh yes, well locally it will look flat, but actually on a much bigger scale, it will actually have to be like this. Where do you once you think you have the understanding, do you understand that, no, actually on this scale we need something else?
This is the thing. There's no concept of scale by design in the manifold. The scale is additional structure. It doesn't necessarily exist. So when we talk about an ant as a vision, you have to add the fact that, like, ant lives in a fog. It doesn't have a straight side to the other area, and it doesn't it has only its own foot to scale stuff, right? There is no scale in general. But it already has some curvature inside if it needs to measure it, it's a local one. So there is this intrinsic properties and there is, like, global properties. And so transitional functions are needed when you try to, like, define global structures on a manifold, and then, like, based on type of transitional functions, you are more free to define more structures on the global manifold or like less. Like, you can define size if the functions are good enough. You can define orientation if the functions are good enough, and so on. Yeah.
Thank you for your talk. Is there some sort of definition on when you have a complete set of transformation functions to define the manifold from the perspective of the ant?
Like, what is... we need to define what complete means here. The thing is, like, you have a manifold, you start from a set of points. And in the definition of a manifold, we say every point has to have a chart next around it. And when we say transitional functions must exist, they must exist for each pair which overlaps. So the complete set means, like, each pair of charts has a smooth transition, and all of these transitions are aligned to each other. But there is, like, from here you need to go to the area of, like, compact or non-compact manifolds, because your manifold can have an edge, sort of, like, and then your chart just goes till the edge, and then there is a gap. these manifolds exist, and they are open manifolds, and they can be there. But if you want complete manifold, like compact one, which is like smooth all the it is smooth all the way, but yeah, it's really compact, so there is no edges. Then you have additional requirement, and so these transition like none of the charts should have just an open edge without an overlapping chart sitting there. So there should be like overlap everywhere. sorry.
I have one more question. Are we humans all donuts?
We are, I think, humans, but like the funny question is in which dimensional space we are living, and like we're used to three-dimensional one and the time and some other dimensions and so on. So, yeah, this is like perception of dimensions for humans and real dimensions. This is where the fun starts.
Are there some other questions? Oh, there in the front. There's one. I'm coming.
Thank you for your talk. Can you give like an intuitive example of a manifold which is not smooth or not differentiable?
Which is not smooth?
Yeah.
Take a cube. It has edges.
Yeah.
It doesn't have a smooth function going over the edge of a cube. It can be like approximated with a smooth manifold, but whenever you have an edge, like an actual edge here, this is not smooth. And this means it's not differentiable at this point. So it still can be covered by overlapping charts, but the transition functions will not be smooth. They will be like module function. So there will be a point where there's no derivative. There are like more exotic examples, which I probably already forgot. But yeah, this one is more obvious. On like whenever you have an angle, this means not smooth. Sorry?
Okay, you can hear me. Great. Thank you, Alexandra, for the presentation. And have a big applause for her. All the questions.
Thank you.